Hello everyone. Today's agenda will be Darboux's theorem, the intermediate value theorem for derivatives. So before we start, we'll be taking a look at two short sections, the first of which is an introduction to the intermediate value theorem, or IVT for short. First of all, to get a rough understanding of how it works, imagine a polynomial function fx. Can be cubic, quadratic, anything you like. Then think of a closed interval from a to b along the x-axis of the function. Now in that interval, we can simply choose a point that has y coordinate, and if the point with y coordinate of that function is inside the interval function from a to b, then we can say it is continuous. Take this figure for example. In between a and b, there exists a point on the function with coordinates cu such that u is in between fa and fb. Next, we shall discuss a little regarding other theorems that hold in order to prove Darboux, and these are the IVT for general cases and MVT, Mean Value Theorem. According to the theorem, if a function f from a to b on R is continuous and is differentiable on the open interval ab, then we know the value of f prime x naught is as such. Let's see why. First and foremost, we'll be needing these two functions with the same domain as function f. Gx is defined as such. And make sure to note that gx is in fact a straight line, a linear function from points a to b on the function. Then we have hx equals to fx minus gx. The important characteristic of hx is that at points a and b, hx equals to 0. Now, this factor is what we truly want so that we can apply Rolle's theorem. This theorem is used to find that g is continuous on closed interval ab while also differentiable on open interval ab. Thus, there has to be an x naught in a ab such that h prime x naught equals to 0 because ha and hb are same. With these two equations in mind, we also want to know that we can perform certain calculations. First, differentiate both sides of equation 2 and substitute equation 1 to gx. With some simplifying according to the laws of derivative, then we let x to be x naught. We can obtain line 3 from line 2. And remember, as h x naught is 0, its derivative is 0 as well. The other constants will also be 0 after the derivation at line 2. Therefore, we get line 4, which now concludes the not so rigorous proof of mean value theorem. Anyway, remember the intuitive idea from our introduction? The IVT for general cases is a theorem which states that, given a function y from a to b on R, for any c in between a and b, there exists a yc which equals to k, whereby k is an element of function y from a to b. This implies that the function y from a to b is convex and thus an interval. Now for the long-awaited main course, Darboux's intermediate value theorem for derivatives. Before moving on, I would like to state that we want to recycle some letters and notations. So try to forget everything related to, say, A, B, C, or F, or G, or H, okay? Then, here's the definition of the theorem. Well, you can read it yourself, right? Done? Okay, so basically, the theorem asks us to check two things first. 1. This function f is continuous on ab, and it is differentiable as well from a to b. 2. F prime plus a and f prime minus b exist but not equal to each other. Still following? So, if we know these two, then we know that for any c in between f prime plus a and f prime minus b, there must be an x naught such that f prime x naught equals to c. See the connection? So basically, Given the above two conditions, we can deduce equation 3. This is Darboux' theorem. Alright, time for some rigorousness. The first thing to do is to define a function gx with a domain similar to f. When x equals to a, it is prime f prime plus a, or if not, then fx minus fa over x minus a. Then limiting x to a plus on function g, we find it equals to f prime plus a and also ga. And voila! G is continuous on the closed interval ab. Quick question though, do we know that the endpoints f prime plus a and fb minus fa over ba are in the interval of function g from a to b? Actually, yes, by defining the open subinterval of ga to gb and using the IVT, it is indeed true. Then similarly, we can define hx and kind of swap around a and x, then replace a with b and so on. Then we get hx. But note that when x equals to b, gb equals to f prime minus b. As such, h is continuous on this interval and contains the endpoints as well. Here, we have a simple illustration of the intervals of functions g and h from a to b. It is important to know that their endpoints are included in each interval. Finally, the last step. Remember the three endpoints? So, if there exists a c in between f prime plus a and f prime plus minus b, then we know that it is strictly in either interval HAB or GAB. Now stay with me, we're almost done. Without loss of generality, we let C to be in HAB. So since X is clearly not B because C is in between HA and HB, then we know for a fact that C equals to FB minus FX over BX. And thus, by MVT, there must exist an X0 in closed interval X to B such that F prime X0 equals to C. In summary, given that point A, F restricted to the closed interval of A to B on R is continuous and that F with open interval AB is differentiable. So that's point 1. Point 2, F prime plus A and F prime minus B exist but are not equal. Then with these 2 points, we can come to the conclusion that for any C in between those 2 endpoints, there must be an X0 in open interval AB such that F prime X0 equals to C. And there you go, ladies and gentlemen, we have proven for ourselves Darboux' intermediate value theorem for derivatives. Thank you for your attention and have a nice day.